When we're looking at rocks, how do we know how old they are? This might conjure up images of expensive labs with particle accelerators and so on, but the reality is a lot more mundane. What we really depend on is a bit of knowledge and the ability to tap into the work of everyone who has got us to this point over the last 200 years. But the best bit is that anyone can do this with a bit of experience and practice and willingness to have a go at it. Hello again, and welcome back. And welcome back also to my beard ornament. Yes, I know, but some of you liked it. And this is apparently the best way I've got of dealing with the audio problems that I know some of you have been having with the rumbling background noise. Doesn't happen on all systems, but some people hear it and others don't. Anyway, this I hope will have eradicated that and will still be pretty good quality sound for the rest of you. So let's hope this works. All right. On here, we sometimes do quite technical things, deep dives into papers or areas of paleontology that are barely covered even in degree courses. But other parts of it are much more about the background, the introductory parts that get people up to speed in the basics of how this subject actually works. And one of those areas is how on earth we actually date rocks. How do we walk up to an outcrop and say, aha, it is Ordovician? And it might seem like a bit of a dark art, and some people might assume that in order to get this sort of age and say that it's 473 million years old, then you need a big lab and something like a mass spectrometer to get to the answer. And the answer is that somebody has to have had that. But that's not what we're doing when we go and identify the age of a rock. So let's start at the beginning. Imagine you've been dropped off by helicopter, blindfolded, somewhere in the vast reaches of Siberia. If you're from the vast reaches of Siberia, then congratulations and welcome, but hard luck, you're going to Argentina instead. Or maybe Mali. We'll have to see. Anyway, it's remote from your perspective. Once you know what you need, you can ask for papers by satellite connection, but until then, you're on your own, with some rocks and a little basic microscope. Obviously, you can't get very far without that. We're not cruel, you know. And so, you are surrounded by a variety of rocks. How do you work out how old they are? Well, there are easy ways and there are hard ways, depending on what you've got. And sometimes there aren't any ways at all. But let's assume there's something. In fact, let's assume to start with that you've got lucky, and there are a wide range of rock types all around you. You've got sandstone layers and mudstone and some lava flows with volcanic ash beds scattering through them. And let's also assume that it's not all been metamorphosed. If you've got sort of high-grade metamorphism that has cooked the rocks, recrystallized them, bent them all out of shape so you can't see where the original bedding was, then you've got problems. That's what a lot of Precambrian geologists have to work with, going back into the really deep, early history of the planet. But we're not them, luckily. If you've got nothing to work on, then you'd probably have to map the whole region at that point and just hope to find something above or below your layer that's datable to some extent. But you don't have to do that today. Now, volcanic ashes and lavas are really useful if you've got a mass spectrometer handy, which sadly you forgot to put that in your pocket. Oh well, we'll have to do with something else instead. So just in case though, you might want to take some samples of them, especially a nice fresh volcanic ash bed, which is you sort of scrape off all the surface layers and get inside where it's not totally weathered, and get a nice lump of that out, put it in a sealed box in a Ziploc bag, label it carefully, and take a photo of where it's from so you know where it fits in the rest of the sequence, and put that to one side. You can take it back with you. That's not what we normally do in the field, though. So for the normal approach, we need sedimentary rocks. And specifically, we need fossils. So fossils are actually extremely common. They are not rare things. In most sedimentary environments, some fossils will have formed. That is not to say that most things that lived in those environments have been fossilized, because that is absolutely not true. But what we see in the geological record is a sort of condensed sequence, if you like. So there might have been millions of organisms that lived and died in that environment and were ultimately destroyed. Their shells were broken, dissolved, washed away, and you see no trace of them. But despite all that, one or two of them survived. And so you end up with fossils of at least some proportion of the life community. It's actually quite a good thing, because I think it's been calculated kind of anecdotally, but don't quote the numbers on this, that if you were to fossilize everything that is living today on around the coasts of the world, then the Earth would run out of carbon in 10 years. So be thankful that things don't get fossilized on that scale. Okay, so you're looking for fossils. And let's say you start off with these nice thick sandstone layers. Luckily you brought a hammer with you because you're going to need it. And you start breaking the sandstone down, and what you find is not a lot. Eventually, though, you get lucky and you find this little layer with fragments of shells in them, which is great. That means you've narrowed it down to the last 1/9 of Earth history, because we don't get shells until the Cambrian. Okay, so rather than being somewhere in the vast expanse of the Precambrian, we've got a rock that is aged somewhere between the Cambrian and the modern. We can narrow that down, though, surely. Unfortunately, in that case, you haven't hit the gold mine. You've got little fragments of phosphatic brachiopods. And phosphatic brachiopods evolved in the early Cambrian, and they're still alive today. They're not nearly as common now as they were in the Paleozoic, the first sort of 250 million years since the Cambrian, but they're still there, and you find them in the Jurassic and so on. So getting a sandy layer with bits of fragments of these shells in, you ain't going to get any further. But still, it's a start. And of course, if you find different types of fossils, they might be a lot more specific. Ooh, now that looks a little bit better. You've got here a bit that isn't a phosphatic brachiopod. That's a bivalve. It's very poorly preserved, as you might expect, because the shell is dissolved and you've just left with this sort of impression. And that, unfortunately, is not what you need for identifying bivalves in detail. But we do know that bivalves did exist in the Cambrian, probably, but they are very tiny. They're very unusual small things. And then they appear properly in the early Ordovician. So we have here evidence that it's probably not going to be a Cambrian rock. You've got something from the Ordovician. Well done. Well, Ordovician or later. So we've narrowed it down now to about 495 million years up to the modern. You're starting to see how the principle works, though, right? The more precise you can get, the better you can identify these fossils, the more we know about that group that you've identified, the better. So some rocks, like sandstones, normally preserve only relatively poor fragments, and this is because they formed in quite turbulent aerobic environments where there's a lot of water movement, things are being washed around, exhumed, washed around again, buried, and basically it all gets broken down. So a sandstone is not your best bet for finding a useful identifiable fossil. Sometimes you do, of course, but usually it's a little less promising. Now, limestones can be much better, or they can be awful. If you've got an acid lab handy, then you can normally dissolve a limestone over a few months and get lots of really interesting things out of it that you can do something useful with, but you haven't. Sorry. If you're looking at limestones in the field, then it depends on the limestone. And sometimes you get things like coral reefs in limestones, where you have beautifully preserved things in 3 dimensions. And yes, it's an absolute pain to get a good specimen of them, because they normally break through the middle. You get a cross section, which might be what you want, or it might not. But limestones, I personally am not used to working on normally. And so I find them difficult to identify the fossils in. Other people are really used to limestone, so they would go straight at them and try to break them open and find a trilobite or something like that. But they probably have a bigger hammer than I do. And they also have the downside of they've got to carry all this stuff back again, and limestone is heavy. It comes in great big lumps, rather than nice little handy bits of shale where you can get 100 fossils in a small bag. I like shale. So let's go to the shale. The mudstones are generally laid down in relatively quiet conditions, and they often preserve quite a wide range of fossils, normally quite well. So it depends on the environment they formed in, but in general, mudstones can be really quite good for the sort of thing we're looking at. You want lots of fossils quickly? Go for your mudstones. Of course, in paleontology, you've always got a pretty high chance of finding something new, especially if you've gone to a remote area. Sorry about that. And what you want for this, to date the rocks, is not something new. Something new is actually pretty useless unless you can tie it down to a particular group. So a new species of dinosaur, yeah, okay, you've got a Mesozoic rock. But in this case, what you're looking for to get it really pinned down precisely is something that is very well known. The reason this matters is that if we know the species, we can look up previous papers that described it and recorded it from different places. These papers will assign ages to them as far as they possibly can, and if you know that you have a particular species, then it should be around the same age as the previous occurrences, because most species only lived for a few million years out of this 500 million of the Paleozoic. But how do we know the ages of them in the first place? This all sounds a little bit circular. We know them because we have a body of work that stretches back centuries and is still ongoing. To understand this, we've got to go back to the foundations of geology, effectively, and how it has built up since then. So there are a few absolutely fundamental critical aspects of this that we need to get straight at the beginning, which may be basic to a lot of you, but not to others. Firstly, sedimentary rocks are laid down in layers, each on top of the one before. So you go up through the sequence, you get younger. There are, however, gaps, lots and lots of them. Sometimes there might be thousands of tiny gaps in a short sequence. Sometimes there might be one gap, which lasted for hundreds of millions of years. So the sequences are never complete. We never have a complete geological history in one place. It just doesn't happen. But we have enough little bits of it that we can put together quite a lot of detail. The fossils within those rocks, quite obviously, were the remains of organisms that lived at the time those rocks were deposited. Almost entirely. You can occasionally get old fossils reworked into younger rocks, but ignore that for the moment. In general, the fossils represent the ages of those layers that were laid down in sequence. So fossil groups, from kingdoms down to species, have a range in time, which can be quite short. You can have a species that only lasts a matter of tens of thousands of years even. But these ranges can also be extremely long. I mean, there is the genus Rhabdopleura, which is the modern graptolite, effectively, which appears to have survived from the early Cambrian up to the modern and is still recognizably the same genus, or at least it's not distinguishably different. So they have ranges. They also have a range in space, so you can have endemic species that exist in only a very small area that evolved on a single island, for example, or you can have things that cover virtually the whole world, at least for one climatic zone. So because of all this, there is a succession of rock layers exposed across a region, and you can look at the fossils found in one layer and see that they are quite consistent. You can find the layer below and see what's in there. You can then, if you happen to be a canal engineer on a mission, map out these consistent layers that were laid down in sequence and produce the first geological map, color-coded by noticeably different rock types. This is exactly what William Smith is famous for having done and published in 1815 the first geological map of mostly of England. The distinct units were named in various ways, but mostly descriptive. So for a thick sequence of coal-bearing rock that he described as Carboniferous, the name stuck permanently. A lot of these names actually remain as geological formations, such as the Oxford clay or the cornfresh. But at this time, he was creating these names and describing distinct units of rock. At this time, we didn't have a concept of geological periods. The geological timescale didn't really exist in any sensible way, but only units of rock that could be recognized and correlated from place to place. That soon changed though, and with this geological map and the mapping out of separate units within a sequence, people started to name particular sections of the column composed of multiple units after places where they were well known. So the Jurassic was named after the Jura Mountains, the Devonian after the rocks of Devon, and so on. So these units represent both thicknesses of rock and intervals of time during which those rocks were laid down. This was the start of the geological timescale. Although it was a long time before we could actually put an age on any of it in millions of years, we had the beginnings of a relative chart of time represented by the rocks. Recognizing these time periods relied on being able to correlate layers of rock. If we use the nature of the rock itself, so a white limestone called chalk, as we can do across many parts of England and in fact extending onto large parts of northwest Europe, in the Cretaceous at least, then this is known as lithostratigraphy. Stratigraphy is essentially description of layers. That's what it translates as, and that's what it is. We're talking about describing the layers and correlating them. Lithos refers to rocks, so lithostratigraphy is correlating layers of rock based on the type of rock they are. And this is the basis of geological mapping. It's what you can normally see in the field immediately. You recognize a rock layer, and then it changes into a different rock layer, which has a different name, and you can map that boundary. So that's the fundamental basic one. But some of these rock layers can be very thick in time. Some of them can go on for tens of millions of years even. And they can also vary laterally through time as environments change. So as sea level changes, a rock layer that represents a certain water depth moves with it. So they don't necessarily represent the same time. It's a start, but it's really not ideal. It also doesn't help you if you want to correlate things in different parts of the world, because the rocks laid down in one tectonic basin or one ancient sea are going to be completely different to the ones laid down in another area at the same time. So you want something to correlate these layers with that is independent of the part of the world that it's in, something that can traverse across continental boundaries and be found at the same time worldwide. What you want really, in other words, are fossils. Some groups of animals and plants fit the bill perfectly. Others really don't. So, for example, imagine a specialist mite that lives on mountaintops. And these are highly unlikely ever to be fossilized. Any fossils that are somehow miraculously formed will then be eroded again as the mountains disappear over geological time. And even if by some fluke of circumstance you get a fossil formed and preserved for posterity, the thing living there is not going to be the same as anywhere else in the world, probably. So it's going to be endemic, and you can't correlate it because you'll never find it anywhere else. So there are a lot of things, particularly land-dwelling creatures, that are restricted in their ranges, and they're not much use for correlating. But things that live in the sea can be much better, especially things that live in the plankton or in the surface water. So nekton are swimming creatures as well. But plankton and nekton can cross wide swathes of ocean, can be found abundantly, and can turn up in different places around the world. And so they can be used to identify different layers within these major layers of rock, and have been extensively. So certain groups have been studied in much more detail than others because they're just good for this job. And ideally what you want are marine creatures that are ideally planktonic or pelagic. They are abundant, they're diverse, and they have a dynamic evolution. So a species doesn't last very long and it gets replaced by other species very rapidly. If you have all that, then you've got the model for a really nice system of working out which layers of rock you're looking at. And there's no one group that does this job for the whole of the Phanerozoic since the Cambrian. Um, but there are lots of groups that can be used for certain intervals. There are more specialist ones as well, like in the Carboniferous, some of the best uses are for plants. But for marine creatures, we have things like ammonites in the Jurassic and Cretaceous, which are used very extensively. Trilobites are used commonly in the Cambrian. Even if they're not planktonic, they still spread across quite large chunks of ocean, and you can map out from one area to another, and find a chain of species that connect to each other. Various groups of microfossils are also very widely used. Now, this is a specialist technique because you have to usually dissolve the rock in some sort of acid and then look at things down a microscope, process them, and so on. But once you've done that, the fossils are normally very abundant, and they're usually planktonic things which can spread across wide areas of the world. So these microfossils are a specialist technique, but very, very useful. You can also find a lot of fossils in a small sample, which is why the oil industry uses them a lot. So you get your well core going down, and it throws up chips of rock back up the core, and you can then analyze those chips of rock as they come out. And I know we've got at least well-site geolog on here who has done that for a living. So microfossils are great, but you haven't got an acid lab. Sorry about that. So we're going to have to go for some other group. And one of the groups that is extremely useful for this in the Paleozoic, at least in the Ordovician and Silurian, are the graptolites. Now, I happen to have a graptolithologist on hand, so I'm not allowed to do anything else. See what I mean? She's always checking up on me. Right, okay, we can go back to sponges now. We can't go back to sponges now. Graptolites, yes, graptolites are definitely where it's at. Graptolites are actually ideal though. They're planktonic, they drifted around the surface oceans, they're extremely abundant, they're quite low in the food chain, so probably feeding on algae and zooplankton, and they were preserved in their billions in mudstones from the offshore environments, even up into sandstones and limestones. So because they drift in the water, they are independent of the environment. You can find them pretty much everywhere in marine rocks. And they also have extremely useful evolutionary patterns. They're very diverse, and many of them live to a very short length of time. So they're actually ideal for correlating rocks in the process we call biostratigraphy. So mapping out of layers by biology. Well done you. Just a few minutes scrabbling around in the shale, and you found yourself a graptolite. There you go. It's quite fortunate that it happened to be the right age, isn't it? But, well, these things happen. So you have here a little graptolite, and it's a single branched one rather than a big bushy thing, so that means it's a planktonic one. And that is one of the groups that evolved relatively later. So graptolites evolved into the planktonic forms at the base of the Ordovician, then carried on through the whole Ordovician, Silurian, and into the Devonian. But in this case, we can narrow that down a lot further at a glance, because it's a single branch, and this single branch has thecae only on one side, these little tubes, a sawtooth on the one side of it, not on both sides. So that means that it's Silurian, possibly early Devonian, but basically we're looking at the Silurian. So that's already just the basic bit of information about the ranges of different types of graptolites. You have an immediate answer. We've got something which is almost certainly Silurian in age. Not bad going. But we can probably do a lot better than that. So over the last 200 years, we've not just been looking at the periods that were defined all those years ago, but also subdividing them, documenting and creating a much more detailed timescale. So the rocks have been divided up into smaller and smaller intervals. They've been compared across regions, and there is now a coherent geological timescale appearing, which has been developed internationally. So we now divide the Ordovician into stages like the Darwinian and substages, and the Silurian into intervals like the Wenlock and Ludlow. And these have subdivisions as well, and even though the rocks usually don't show any reliable changes on that sort of scale, these subdivisions are based largely on fossils. So graptolites thrived in the plankton for those 80 odd million years, and in that time they changed quite a lot. There are thousands of different species with slightly different morphologies. Sometimes you have to measure differences in the spacing of the thecae, look at the shape of them, look for spines, and so on. And so we can pin it down a lot better than just being the Silurian if we can identify which species or genus this belongs to. And we can. So when we look at this in detail, you can see that there are little spines coming off these thecae. The thecae are also particular shape, which is different from those of other ones, and all of this leads to it being a thing called Cetograptus. Now, Cetograptus only existed, as far as we're aware, in the Ludlow, which is a stage of the late part of the Silurian. So now we're narrowing it down really quite a lot. We've got it down to an interval only about 5 million years thick. Now, the name Ludlow comes from a town in the Welsh borders where the rocks of that age are particularly well represented. Now, the Ludlow itself is subdivided into the Gorstian and the Ludfordian, and then each of these intervals is again further subdivided into what we call biozones. Now, biozones are basically the smallest unit that we can see reliably in the rock record, and they are characterized by particular assemblages or fossils. And you tend to have biozones based on microfossils of one type or another, or of trilobites, or of, in this case, graptolites. And when you really go back to the literature, don't forget you can phone in that satellite call for a nice little guidebook to graptolites of the Ludlow, or at least a few papers. Then you should be able to work out which species you've got here. And it turns out that what we have here is Cetograptus incipiens, which is restricted to the Cetograptus incipiens biozone. We've really done quite well now. This biozone is probably less than 1 million years long. So out of the entirety of geological time, we've got a few species of graptolite, or one species of graptolite, has narrowed it down to about 1 million year interval. The problem is that that is based on our understanding of the range of Cetograptus incipiens in the rest of the world. It's never been found outside a particular zone or particular range, so we assume that if we find it somewhere else, it is found in the same range again. That doesn't necessarily follow. We're often finding a species which occurs slightly later or slightly earlier than its previous known occurrences. So we don't just stick to one species. Ideally, what you want is to find as many species of graptolite as you can, identify them all, and then see where the overlap lies. Because if this particular species is outside its normal range, we should see that it is co-occurring with other species that are not normally in the incipient zone. So when you have multiple species, you look at the overlap of them all, the known range overlap, and you see how consistent it is. And by doing that, we keep refining the biozonation, the ranges of the species that are known, and we end up with a really solid system, as long as we know them well enough. And for graptolites, we do. New species still keep being found, but not at a very rapid rate, and most of the time you can just go to the species that you identify, and you can pin that down into fairly confidently a very narrow slice of the geological column. And these faunas will vary not all that much around the world. We can find some of the same species here and in Australia and China. So because they floated around the currents, you can look at other regions of the world in the same sort of latitudinal zone, and you should find a lot of overlap in the species, or at least enough to be able to be fairly confident on the age. And that's basically that. You find the right fossils and have the right knowledge or the right books, and you can get an age worked out amazingly quickly. Because of all the generations of paleontologists and geologists that have been putting together this huge resource of literature that allows us to then slot our new observations into the existing knowledge. Starting from scratch would take a long time, but we don't have to because of all this work that's been done before. And that's it in a nutshell. Biostratigraphy is, in principle, a very straightforward approach. It's just that to do it well, you need a lot of knowledge and you need to actually put the work in to go and find the right fossils. And some time periods are easier than others. Some environments are much easier than others. So I suppose we need to start thinking about the cases where it wasn't quite so easy. Sometimes you'll end up in an area of freshwater deposits, so lakes and rivers and ponds and so on, and then you'll be unlikely to find anything that can really be tied to an existing biozonal classification scheme. The freshwater ecology is much more restricted, it's endemic, it tends to be rarely preserved in the long term, and we just don't have the links from one region to another. So if you've got an area where there's a lot of freshwater deposits over a wide region, then you can develop a biozonal scheme within that region. But it's very hard to tie that to the rest of the world or work out where it fits in terms of the global biostratigraphy. There are often clues, though, and if you find any plant fragments, for example, you know it's late Silurian at the earliest. Find specific groups of plants, and you can narrow it down a lot more. Of course, you also get things like wind-blown spores and pollen. So if it is after the point where, say, flowering plants evolved, or some of these trees which have wind-blown spores, then you've got a chance of being able to tie it in that way. But it relies on microfossils at that point, and you just don't have a more general pattern to be able to look at. But what if you can't find any fossils at all? Well, then it gets much harder. At that point, it's a matter of constraints as far as you can. So you map out the whole area, follow up and down through the sequence until you can find a layer that gives you some sort of clue as to what age it is. If not directly, then maybe you can correlate with other layers in a wider region, maybe even 100 kilometers away, where you have found something that can be dated. And it's when things get this desperate that we start looking into the other stratigraphies. So there is chemostratigraphy, which measures things like oxygen isotopes through a sequence of limestones and then tries to match up variations in the global oxygen isotope composition of the atmosphere and seawater, looking for recognizable anomalies that have been detected in the global pattern elsewhere. So when there is an ecological crisis, for example, you get a shift in the carbon isotopes because the way that biomass works and carbon dioxide is drawn down and recycled through the ecosystem changes. So you get a spike in the ratio of carbon-13 to carbon-12. So chemostratigraphy can look for things like that. It can also look for changes in things like strontium isotope ratios, which is a reflection of things like the weathering rate of mountains. So you tend to have very elevated levels of something or other when you have a lot of mountain building and erosion of it. So there are ways of trying to tie into global patterns, which can either be quite short-lived events, little mass extinction events, for example, or they can be long-term changes in the biosphere and the geosphere as a whole. The problem is that there are so many changes over time, including spikes in different directions, that it only really works if you already know which general interval of the column you're looking at. If you find a spike and you know you're in, say, the Ediacaran, then you can start to narrow it down much more precisely. But if you don't know where you are at all, then there could be many different spikes to choose from that you can correlate it with. So it gets much harder at that point. There is also sequence stratigraphy, where you look for a regularity in the changing of sea level, which is reflected by the type of sediment that's deposited. So as sea level drops, a marine deposit will tend to become coarser because the coastline is getting closer to where you are. And you can map out those changes and correlate that sequence with what you see elsewhere in the same basin. So, of course, this doesn't really apply outside that because it's not just global sea level that's affecting it, but also local tectonics. So the area of the crust going up and down and so on. So that can be really useful, but only really locally. Magnetostratigraphy is the correlation of magnetic field polar reversal, so when north and south flip. And that can happen on a recognizable sequence of intervals. So in relatively young rocks, and we are talking really quite young at this point, you can actually match up that sequence like you do with tree rings and be able to work out exactly where you are there. But this doesn't really work going back into the deep past, because then there's too little known about the magnetostratigraphic sequence, and there are too many reversals to try to match up with. There's also a really useful one potentially, which is event stratigraphy. So in this case, you're not looking for patterns that you can take anywhere and match up with the same patterns everywhere else. You're looking for individual events that leave a mark globally. So we're thinking about things like the Chicxulub impact event at the end of the Cretaceous, which left a layer of iridium over the surface worldwide. And you can find potentially those unique one-off signals that are distributed globally. And they're one of the very few types of stratigraphy that give us an absolute tie point between here and somewhere else a long way away. Because even fossils migrate slowly around the world, and the first appearance of one species in one continent will be a slightly different time to the first appearance somewhere else. Normally that is within the range of the error bars that we would expect to have anyway, that it's small relative to timescales we're dealing with, but it's still a difference, whereas these event deposits can be a single marker for an exact event. And huge volcanic eruptions can do this regionally as well, and you can see those in the geological record. But what if all that is hopeless? What if you're surrounded by obviously old deposits, and it's mostly sandstones, and there's nothing in them, and you wander around increasingly despairing at ever being able to solve your problem between crags of sandstone and volcanic ash, and the surrounding areas are covered by impenetrable bogs as far as a helicopter can see. What can you do? Well, you go back to those volcanic ash beds. Here we're actually going out of the field of stratigraphy and into geochronometry. So we're no longer trying to correlate at this point. We're trying to date the rocks directly. So at this point, you're starting to look for igneous layers that were laid down within the sequence. So if you have an igneous intrusion, that's coming up after the sequence was deposited and intruding into the surrounding rock. And this happens a lot, but you also get lava flows that flow out over a layer of sediment and then are covered by more, and you get volcanic ash beds. And these igneous deposits usually contain crystals of things like zircon. This is a zirconium dioxide. They form really tough little crystals that you can extract from volcanic ash beds just by sort of washing the mud and picking out the tiny crystals that remain. And zircons in particular are really good because they contain lots of trace elements. And these traces include radioactive elements that were incorporated into the crystal structure. Now, for radioactive isotopes, we actually know in most cases quite precisely what their half-life is. We know how quickly they decay, or the half-life is exactly the time it takes for half of the atoms in a sample to decay. So it's statistical, but it's very precise because you have a lot of atoms. And if you can measure the amount of atoms that there are left and the amount of the thing that they decay into, and you can fulfill a few other constraints as well, you can calculate quite simply the length of time that is elapsed since that crystal formed and those original radioactive elements were included into it. And there are various systems for doing this. It's basically the same sort of principle as for carbon dating, but that only works back, say, 50,000 years or so. For these geological timescales, you need things like uranium, lead, potassium, argon, and various others. And the really nice thing is, because we have multiple suites of radioactive systems to look at, we can compare them directly and you get the same results. There are always error bars. So you might find that your results are something like 556.3 million years plus or minus 2.7. That's actually quite a good one. But there are error bars which are significant, but the more that we start to do this sort of analysis, the more we can narrow down those error bars and actually get a precise date for the boundaries that we're interested in. So you do this analysis, or rather you give up on your assignment and go home with some nice little samples, and then you do the analysis, and you come up with a date of, say, 419.3 million years plus or minus 5. And what this tells you is that it is in the late Silurian, which is convenient because, of course, your other you found some graptolites which confirmed that. But in this case, you've got a date which we know is late Silurian. But how do we know that's late Silurian? Because people have taken this geological timescale with all its subdivisions and all its biostratigraphic zonal schemes and so on, which is so well worked out, and they have calibrated that timescale by going to sites where you have a sequence of graptolites and volcanic ash beds. And you can take that ash bed and say that, well, this is around the base of this biozone, and we can date that to this particular number of millions of years. So eventually, when you have enough of those measurements, you get a pretty good idea for the sequence of ages, the dates that can be put onto this timescale. So field geologists don't actually tend to think that much in terms of millions of years. We know that those numbers exist, and we might have a pretty good idea of exactly when the time periods that we're particularly interested in were. But that's not what we work with on a daily basis. We work on biozones and formations and so on. And so what the public generally assume is that I think we're thinking in terms of 417 million years all the time, but that's not the case. That is a calibration that is superimposed on top of the timescale that we actually use as a general basis. And we don't walk up to a rock and sort of magically read that it is 418 million years. What we do is use all the tools at our disposal, the fossils, the type of rock in context of the surrounding area, any evidence for events and so on. All of these lines of evidence can come together depending on what is present in that particular rock. And then that is what allows us to tie it in with this global geological timescale, which is then calibrated, and therefore we know roughly what the dates are. And I still remember times only 20 years ago when this was still in its infancy, this dating of the various units. So you have a date that is calibrating a boundary that is above a boundary below it, but the date given to it is actually older than the one below it, which we know was wrong, but the point is that we didn't have enough constraint on the error bars. I think that's mostly been eliminated now, so generally it's much more coherent. And we're looking at differences of a few million years here and there over hundreds of millions, but it was still quite amusing when you saw it. So I hope that gives you a better idea into how exactly we go about dating rocks, what the whole geological timescale is, and why you never see the whole lot in one place, because that's just not how it works. The timescale is this abstracted composite of everything that we have learned about the history of the world. So we've been able to do this now because we've had a couple of 100 years of really dedicated work putting it together. If you want to do this on Mars, then I recommend you want to do something else. In that case, there are actual geological maps of Mars with relative dating of various rock types and even attempts at absolute dating. But it's done by clever little tricks like looking at the density of impact craters, because those also build up over time because of the rarity of impacts. So the really heavily cratered bits are much older, the younger bits are less cratered, and you can work out things like that on other planets. But it's all the same sort of principle. We know there is an abstract geological or Martian timescale, which we then have to try to break down into units that we can actually correlate in practice and work out approximately the ages of. It's a really fun puzzle. It's sort of multi-dimensional jigsaw, and it's much more complicated than you might think, but at the same time it's also simpler, because it's not actually about dating. It's about correlation. It's about being able to recognize that this is roughly the same time as this. I will leave it there, I think. Thank you for listening, and I hope that made a lot of sense. And it's also something that you can do, final thought, wherever you are. It just depends on some dedication, going out looking for whatever evidence you can find. I mean, I know a lot of you probably won't have labs at your disposal to actually do the zircon analyses, but you can find some sedimentary rock, look for fossils, start thinking, okay, when did this group evolve? When did this group evolve? And if you get dedicated, you can start finding books, literature, which will allow you to hopefully work out which species you've got and even pin that down more precisely. So it's a really lovely challenge to do. And much as it's wonderful to have you all listening to these things, I'd love it if some of you at least went out and tried to apply them. It's only when you start to try to do something like geological mapping yourself that you really get to understand all of the constraints, the difficulties, and the sheer pleasure of trying to puzzle these things out. So think about it anyway, and hopefully when it gets back into summer in the Northern Hemisphere, it'll be a good thing to do. Right, see you again. Bye for now.